Alright, this is the algebra section 1.8 titled Represent Functions as Graphs. So our I can statement is pretty much the same thing. We're just taking our functions and making graphs. Alright, so this is just some background information. So if we got one triangle, two triangles, then three, then four. If n is the number of triangles, so we'd have 1, 2, 3, 4, that would be our n. P is the perimeter then. So if you figure out P, perimeter of each of those figures, we could make a table. So for example, we have our dependent variable, which is the P. It all depends on what n is, which is our independent variable. So on the first one, one triangle, our perimeter then would be 3 if each side is one unit. The next one, we have two triangles. If we figure out our perimeter, 1, 2, 3, 4, and then so on. And we get 3 is 5, 4 is 6. If we were to do 5, hopefully we'd be able to figure out from the pattern what would that perimeter be, and that would be 7. And you could keep going. But we want to take that information now to make a graph. Okay, we don't have any negative numbers, so we really only need the first quadrant. Our dependent variable ends up to be on the y-axis all the time, and independent is on the x-axis. So in this case, my numbers are a little off. Alright, I took my numbers out because I couldn't get them to match up correctly. The other ones are fairly close anyway. So, perimeter, whoops, 1, 2, 3, 4, 5, 6, 7, 8. Now when I go to get the next dot, they'll go away. But you know where they're supposed to be, and you can mark that in your homework. So our first ordered pair, 1, 3. Next one will be at 2, 4. Then 3, 5. 4, 6. 5, 7. And 1, 2, 3, 4, 5, 6, 8. Okay, so those, let me see if I can. There they are. I think those are all in the right spot. And if you continue going on and on, you know, your little dots would keep going if you kept expanding your graph. So we don't have a line because we don't have partial triangles. So you don't have like a 1.5 triangle or anything like that. So you just have the dots for this one. Our equation then, if we had to figure out the rule, would be that P equals n plus 2. So whatever the number of triangles is, we're adding 2 to it to give us the perimeter. So our P is like our Y, the n is like our x, and that's then our function. Our equation is our function. P is the dependent variable, n is the independent. Alright, let's try another one. This one we have the price of sliced fruit platters, and we want to figure out how much would a 6-pound platter cost. So we want to look at a pattern between all of these different things. So 1 pound is 210, but 2 pounds is 360. Let's see what I have here. Whoops. Let's go back. So if we look at the difference between 360 and 210, if we subtract those, we get $1.50. If we figure out the difference between 510 and 360, we get $1.50 again. If we subtract 660 minus 510, we get $1.50. And if we subtract between 810 and 660, we get another $1.50. So if we were to figure out what 6 pounds cost, we could take the 810 plus $1.50. And we would get $9.60. But we don't want to have to keep adding this $1.50 all the time. You know, what if we wanted 20 pounds? So we want to have an equation for that to figure out what the cost of a platter would be that weighs W pounds. So this is our W, and then this is our cost, our price. So if P is the price of the platter, this is our P, the weight then is W, that means the price is going to be $1.50 times whatever our pounds are. But we have to check this, because if we have 0, of course it's going to be 0 price. But if I put 1, I have $1.50, and that's not right either. We need like something to add to it. So if we take 210, if we go backwards and think of, well, if it's 0 weight, if we follow this pattern and we subtract off $1.50 off of 210, we would get 60 cents. So we have to add this 60 cents at the end. Sorry, it's so squished. So now if you get 1 pound, if you put in 1 for W, you have $1.50 plus the 60 cents. That'll give you your 210. So it's kind of a weird thing that we have to kind of work our way backwards to figure that out. So our equation then, let me write this nicer. The price of the platter is going to be $1.50 times the weight plus 60 cents. Okay, plus 0.60. Okay, so now question 3 says, how much would a 10-pound platter cost? Use your equation here. Just put in 10 for W. So the price is going to be $1.50 times 10 plus 60 cents. So for 10 pounds, if we move the decimal over 1, we'll have 15 plus 0.6, and that equals $15.60. And then just double check to make sure your answer makes sense. So 5 pounds. If I double the 810, I'd get 1620, and this was 10 pounds, so you know, roughly. So that does seem to be within reason. Okay, so this is just a recap. So our change between each one we said was $1.50, but then we're adding that 60 cents. That was our start value, but we had to figure out the start value by putting in the 0 and working backwards on our table. Okay, here's another one. This time I don't think we have everything given to us. We have a flat rate of $2.50. So no matter how far you go, you have to pay $2.50. But then it's 15 cents per mile. We want to write a linear equation for the charge in terms of the number of miles, and then graph the function. C is going to be the charge in dollars. So here's our dependent. Independent is going to be the number of miles. So no matter how much we go, we have to pay $2.50. So at 0 miles, in theory, we still have to pay $2.50. If we go 1 mile, we're going to pay $2.50 plus 15 cents because it was for 1 mile. So we have 0.15 plus $2.50. So that would be $2.65. Okay, so get a formula for this. C is going to be, you're always going to have that $2.50. Okay, so we're going to tack that onto the end. And then it's 15 cents per mile. A lot of times for these story problems, when you see that it's per something, that's going to involve your variable, your dependent variable. So if you think of it as slope-intercept form, I know we're getting ahead of ourselves, but it's that mx part. Alright, so then I'm going to fill in a couple numbers with our formula here. Alright, so I just filled in a couple of numbers and make my graph. So this would be C, this is your cost, and here's your number of miles. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now it's kind of hard to do the cost here on here. I'm going to go by, I'll try and go by 50 cents. 50 cents, $1. $1.50, $2. $2.50, $3. $3.50, $4. Let me switch to a different color now. So let's see, I know I got 10 for $4 way out here. If you go less than a mile, 0, you got to start at $2.50. And then 1 is $2.65, so that's $2.50, just a little bit above it. Man, this is not to scale very well. Maybe I should throw in some other numbers. Because I hand drew this isn't to scale very well. I threw in another number 4 just to kind of make sure, but because I hand drew this, it's not to scale, so it doesn't look as nice as it should look, like if you were using graph paper, of course. If you're using graph paper, it would look much, much nicer. So we've got our linear equation here, right here, because we had to write that, and then this is our graph. of our function. And yours will probably look nicer when it's on actual paper and you can measure things out much nicer than what I did here. Alright, another one. Man, these notes are getting long. So we've got a car's fuel tank is filled at a rate of 1.6 gallons per minute. So rate, we know that's going to have something to do with the variable. And the tank held 5 gallons of gas before refueling. So before you're refueling, you already have 5 in there. So think of it as time is 0, you have to have 5 in there. So if you have, what else do I have on here? M is the number of minutes, and V is the volume in the gas tank. So V at times 0, it's 5, so you're going to have 1.6 gallons per minute, so you're going to multiply that by M, and then you've got your plus 5. So this is the equation we're going to use for our table. So we'll have M and we'll have V. So these are like our X and Y. Now I'm going to try and pick some nice numbers. So at 0 minutes we have 5 gallons. At 10 we'll have 16 plus 5. Remember, this is as it's getting filled. So that's 21. And let's do 20. So let's see, that would be 32 plus 5. So that'd be 37. Very large gas tank. But this will be enough for us for an example to do our graph. And remember, not drawing these to scale because I'm hand drawing these, just so you know. So V is here, our volume. And this is our minutes, our time. So 0, 10, 20. And let's see, I'll just go by 10, 20, 30, 40, and we'll just approximate as best that we can here. So at time 0, we're at 5. 10 minutes, we're at 21, so just above the 20. And at 20, we're at 37, so just below the 40. This one looks nicer than the last one, a little more linear. I don't know what happened to that last one. And then if you went out further, it would go up further, but you do have a cap here because there's only so much fuel you can put in a gas tank. But this is a nice, simple one that you should be able to do. Alright, and here's your homework. Do the best that you can with all these graphs.